Thank you for having me here. Yeah, the EVA is near and dear to my heart. One of the first missions that I worked as a flight controller at JSC was when the airlock was launched to the space station. So that was a very, very fun mission to be a part of. So I wanted to, let's go ahead and go to the next slide here. So we've talked about Gateway before, but even before that, I wanted to key off of what Dan started with this morning. So how many hikers, campers, backpackers do we have? Anybody going hiking? So I have two teenage boys, and as mentioned, we just recently moved to Colorado, so they really are excited about going hiking. So one of the things, of course, you need in your backpack is your tent. So we started looking at tents, and I said, well, it needs to be small and compact in your backpack, but then it needs to be easily deployable, good use of space, large enough, needs to be resilient, it needs to be able to handle the elements from the rain, the snow, the wind, but also needs to be able to breathe. It needs to be cool when you need it, warm when you need it to be warm. I'm like, wait a minute, I've been to this rodeo before. So Sierra Nevada is designing a habitat for NASA. We thought about a lot of the similar activities. Amazingly enough, we just did our first camping trip this past weekend to test out the new tents. So baby steps before we go hiking next summer. We went to a county park this past weekend. Fortunately, they all stayed warm, got down to about 30 degrees. The tents and sleeping bags worked great. But back to this topic here. So we are one of the Next Step Habitat companies providing a prototype of a habitat to NASA. If I have a pointer here. So here's our modular sequence of build-up activity. We use the power propulsion element, the PPE. Architecture included two of them. One of them would come and go from the gateway. The other one was a permanent member of the architecture. Our ELCM was a dual-use module. It's an airlock. Also serves as part of living quarters and part of the science facility. I'll spend most of my time, though, talking about the life. So this is a large inflatable fabric environment. I don't know who at the company came up with the acronym, but it's a great acronym. It's used in a lot of jokes. Hopefully one day I'll have it on a bumper sticker, but it's our life module. So down in the bottom right here is a rendition of our prototype. Now, we challenged ourselves with this prototype. It's an inflatable, so we made our prototype inflatable. We're actually pressurizing an outer shell with the internal structure inside of it, and you enter into our prototype through an airlock. We wanted to have this element of realism to our prototype and not just believe that we were in an inflatable structure. We wanted to actually be in one. You can see this in this picture in the bottom right, though. Safety factors came into play. We're in 1G environment, so our upper floor had to have railings. We're trying to design out the railings, but that's what that picture showed there in the bottom right. So taking a closer look, this is our inflatable design. It's about 8 meters by 6 meters when inflated. Just like that tent when we're going backpacking, though, we want it as small as possible for launch, so it fits within a 5-meter fairing. When inflated, so there's many ways you can slice and dice an inflatable, right? And we had endless discussions on which way we put our flooring, where we put all of our systems. End of the day, we had to pick an approach and move out with it. So our approach was to instill two floor structures that were in parallel with the core of the inflatable. So it gave us 3 levels, 3 stories. We call the upper deck, the mid deck, and the lower deck. And in our prototype, we're representing the upper deck and the mid deck because the lower deck was too difficult to use in a 1G environment. So our prototype has 2 floors. The core that we call kind of like if you will, an apple. The core houses all of our systems racks and passageway from one side to the other. And out on the floors, we have payload racks and rigid floors for a 1G environment for the crew to move around in. At the end, all of these architectures will be evaluated by NASA when we supply our prototype. We'll see how well this way of slicing a inflatable worked. Now here's a picture of our actual floor layout. Now, as was mentioned, I spent 20 years at JSC, and providing details was something that I am not used to doing. So when I asked my manager, the director of advanced programs at SNC, what do you like me to show? He's like, well, show our layout. I'm like, really? You want me to put that out there? And yeah, let's get it. Let's start talking about it. Let's get out there. We've put a lot of thought into it, a lot of study into how to set up our prototype. So let's get moving out. So similar to how you slice and dice an inflatable, there's lots of ways you can lay out the actual crew space. End of the day, we had to pick a layout and move out with it. It's going to be evaluated, tested. We'll throw darts at it. We'll probably change it. But we need an approach and keep going. So this is our mid deck on the left. This is our main kind of work area. It has lab spaces. We have 2 robotics workstations to support dual operations. We have a bio lab for rodent research, for plant research. And in the bottom right, you can see a mid bay or a sick bay. So this is not only where the crew can go for private medical conferences, they can go if they get injured, but it's also our primary area for human research work. So whenever they need to get sticked and prodded, they can go and do that in the mid bay. The upper deck, we've had to split into 2. Since we couldn't represent our lower deck, our upper deck is actually kind of showing both an upper deck configuration with crew quarters and the lower deck that had the galley and exercise area. So we had to cram both in here. That's why you see, even though our habitat would be designed for 4 crew members, we've only are showing 2 crew quarters in our prototype. You see the galley in the upper right and exercise area there in the left. And given the 1G environment, the yellow on the left and right are the stairs to get up in between the 2 levels. So I'm sure everybody in the room would have opinions on how this could be set out, probably differently than this, and totally agree. Endless discussions in our office on how to do this. We consulted with architects, interior designers, which was interesting, given a bunch of us are engineers. End of the day, we had to pick an approach, move out with it, and evaluate it. So moving on, though, we're very interested in taking this inflatable architecture to new places. There's definitely approaches for the surface of the moon, for the lava tubes, and for the Mars surface and its lava tubes. Even beyond that, I would propose that if the moon's a stepping stone to Mars, that Mars is a stepping stone to Titan. Titan is a fascinating environment, fascinating from a exploration perspective and from a habitat perspective. I've actually written a proposal to look for funding for development of a Titan surface habitat because it's just that interesting of a place to go to. So one of our partners is ILC Dover, and you can see they've already done a lot of prototype work for inflatable architectures, and there's a number of pictures of real hardware they've built for previous NASA programs. So, and these are all great inflatables, but what I'm really interested in is going that next step, the inside. There's lots of questions and debate on what the material of the inflatable should be, and that architecture needs to be pressed forward. We need to keep going in that direction. What are the most mass efficient materials for the inflatable shell, for protecting the crew, for resiliency? That's great. What I'm interested in is, what are you going to do on the inside? Because an inflated balloon does not make a habitat. You've got to outfit the interior of the habitat. You saw in our pictures, we have lots of systems, lots of walls in there that divide up the floors into habitable spaces. How does all that get put into place? That's where we found a real challenge, a real interesting area to go into. So how do you install those walls? How do you put out the fluid lines, the electrical lines, the lighting, the ventilation system in a most crew time efficient manner and a mass efficient manner and a reliable manner? These are the areas I think are the most challenging going forward and putting the real engineering into the dome structure so that this can truly be a habitable space for long-term exploration. So in working with academia and with industry, there's lots of areas here to explore: shape memory alloys, conductive fabrics, self-curing structures, deployable mechanisms, and innovating new ways of deploying the walls, and 3D printing. Certainly, if we could 3D print part of this interior and then have the crew install it, then that's another way of saving mass and volume. So I think lots of innovative areas to go into in this area of inflatable habitats. So that's my message. Thank you.
Question for Bill from the panel.
Looking at both your gateway and terrestrial type, not terrestrial, planetary surface type concepts, do you envision any need for external interfaces, either for science payloads or for EVA, or to enable it to do R&R, any sort of activities like that? And how would you do that with an inflatable?
Yeah, so that definitely is a challenge. We're trying to design out the need for the EVA by having all of our systems inside already. Certainly, the gateway architecture includes a science airlock so that we can transition samples or exterior payloads between the IVA space and the EVA space. Our gateway architecture included an airlock for sure. There was lots of debate on the how often it would be used. We initially had an inflatable airlock, which is an architecture that NASA worked to develop. It's called the MASH, I believe. Where if EVA is something you do infrequently, then you don't need a dedicated module to do it in. You could have something that deploys like essentially an inflatable airlock. You go out through that, you come back in, and you deflate it, and you put it away for later use. If it's more frequent, if we want to do a lot of more construction, more external payloads, then a dedicated airlock module would definitely need to be attached to the inflatable habitat for use.